Welcome to SPT online classes, and here we are going to discuss the theory of magnetism. So we know different magnetic materials. One is ferromagnetism, one is diamagnetism and paramagnetism. Ferro, para and diamagnetism. So here we are going to discuss how it actually works. So means if you take a bar magnet, we know that the magnetic field starts from north pole and it will end at south pole. The question is, how does a bar magnet work actually from the atomic level? Why I am asking this question? Because we know that magnetic field is only created when a moving charge, because of a moving charge, correct? When a charge is moving, then the magnetic field is created. So what about the bar magnet? Is there any electricity flowing through that to create the magnetic field? So that is our question that we are going to discuss today. So if there is no electricity flowing through a bar magnet, how come the magnetic field is originating on the first place? So we have to deeply analyze by dividing a bar magnet into tiny pieces, and we have to reach at the bottom level and we have to see what's actually going on there. So we have to get into a bar magnet. So what we have to do is that we have to divide the bar magnet into smaller pieces. Let's do that. Keep on dividing the bar magnet, we get smaller magnets, so tiny magnets. Once you reach at the bottommost part, you reach in the atomic layer. Now the question is whether an atom is magnetic or not. If you get the answer for that question, then it will be more easy. An atom, which consists of a nucleus and electron whizzing around the nucleus like anything, and we know that when due to the flow of electrons there will be current. Since electrons are revolving around the nucleus in a very fast rate, there should be electric current, correct? So electric current is equal to charge flown by time. We know that I is equal to Q by T is the formula. And we also know that the velocity of an electron around the nucleus is equal to distance traveled by the electron, which is 2 pi r, which is the circumference of a circle. We are taking it as a circular orbit divided by time. So 1 by time you will get it as V by 2 pi r from this equation. Substituting in the previous equation for the current, I becomes I equal to Q by T, right? So Q into 1 by T, which is equal to Q into V by 2 pi r. So now we got the current due to one electron, which is Q into V by 2 pi r, which you can also rewrite as E into V by 2 pi r because charge is electron. Okay, the next point is that we know what is dipole moment. Dipole moment, we know the formula for it is pole strength into distance. Unit of pole strength is ampere meter and unit of distance is meter, so you can also rewrite it as ampere meter square. Ampere meter square, you can split it as ampere into meter square or current into area. We already got the formula for the current due to one electron, which is I equal to E into V by 2 pi r. So what will be the product of current and area? That term you can call it as magnetic moment. Magnetic moment of an electron. Let me write it as MO. Why I'm specially writing it as MO? Because it is now orbiting magnetic moment. The magnetic moment due to the orbital motion or orbiting of the electron around the nucleus, that you can write as E into V divided by 2 pi r. What is the area that it is covering? It is a circle, so it is pi r square. What you're going to get is E V r by 2 is what you're going to get. This is orbital magnetic moment. Remember, it's not momentum, it is moment. Now we know that in any case of circular motion, angular momentum remains constant, which is L equal to m into V into r, from which you get V into r equal to L by m. Substituting in the orbital magnetic moment, you get m0 equal to E into L by 2m. This is the orbital magnetic moment of an electron. Remember, Magnetism is due to moment. This moment itself are of two types: orbital magnetic moment and spin magnetic moment of the electron. Spin magnetic moment, let me write it as m suffix s, which is equal to E into S by m. We know that all planets revolve and rotate around the sun. Similarly, let's take for the time being as electrons are also rotating and revolving around the nucleus. The rotation part you can recoin the term rotation as, say, spinning, and revolution part you can rewrite it as, say, orbiting. So because of the orbital motion and the spinning motion, we are getting magnetic moment, and this is the reason for the magnetism of an atom. So now a particular electron is getting a dipole moment or a magnetic moment. One particular electron, now it is having a magnetic moment. So let me write like this: an electron has got the magnetic moment now. Now, so many electrons are there in an atom. Few of those electrons' magnetic moment will get cancelled out because they are vector. So magnetic moment is a vector quantity. And once you take the case of an atom, what's happening is that there are so many electrons. As I already said, these electrons are whizzing around the nucleus, and few of their magnetic moments get cancelled out when they are paired. Okay, so when electrons are paired, then their magnetic moments will get cancelled out because of their opposite spin. But there are half-filled shells and unpaired electrons. Half-filled shells with unpaired electrons, their magnetic moments will not get cancelled. Okay, we have unpaired electrons and half-filled shells. Their magnetic moments are not going to get cancelled. Those magnetic moment will be, there will be a resultant magnetic moment for all those electrons, for all those unpaired electrons. Their magnetic moment will make a resultant magnetic moment, and now we can call the magnetic moment of the atom. So now the atom is magnetic. Okay. So now you understood how an atom is becoming magnetic. What is the advantage with that? What is the use if an atom is become magnetic? Such atoms, let me take few atoms with dipole moment or magnetic moment. So now all these are atoms. These atoms will be arranged in a particular order according to the mechanism of exchange coupling method. Now that is a quantum effect which we don't have to dig into because that's out of the syllabus. So let's focus into how these atoms are getting arranged according to exchange coupling method, and what next is what we are going to see. Once you can say a collection of atoms, we can call it as a molecule, and now that molecule is getting a particular dipole moment in a particular direction. Now we can say there is a magnetic moment for that molecule. Now the magnetic moment is there for a molecule, or now the molecule is magnetic. Such molecules, when they come together with their particular dipole moment in one particular direction, such space or such region of molecules arranged in a particular direction with its dipole moment or magnetic moment, we can call that region as a single domain. Now this domain is getting a magnetic moment. So now we can say a domain is having a particular magnetic moment in a direction. So let me write like this: magnetic moment of the domain. Now we are going to speak in a larger manner. So imagine these are some domains form, say, D1, D2, with their magnetic moments in different directions. They are arranged in random direction. Okay, D1, D2, D3, D4. Let's call like this: D1, D2, D3, D4 domains with their magnetic moments arranged in absolutely random, and it's not necessary that it should focus in a particular direction. Now what's going to happen is that we are going to introduce the magnetic field. And this is what we call as the external magnetic field. And due to the presence of the external magnetic field, what's going to happen, these domains magnetic moment will get aligned into the direction of our external magnetic field. Okay, so now domains are having their magnetic moments in a particular direction. Because of the presence of external magnetic field, we can say that this particular materials having these domains are actually magnetic, because they are responding to magnetism, because they are responding to external magnetic field. So once you can align these magnetic moments of the domains in a particular direction, and then you can completely remove the magnetic field, and you can check whether these alignments are not changing or not. If they are not changing, we can call it as a permanent magnet. We can call it as a permanent magnet. Or if their alignments are changing after some time, we can call it as a temporary magnet. Magnets like neodymium can arrange their magnetic dipole moments for a much longer time, like some say for years, for some 100 years. They can take their they can keep their magnetic moment aligned in a exactly particular direction, and that's why we call them as permanent magnets. But in the case of electromagnets, once you apply an external magnetic field, it cannot keep its magnetic moment aligned always in a particular direction for much longer time. After that it will change its magnetic moment in random manner once again, and then it becomes non-magnetic. Now there are some other materials, say its domain is completely, say, d1 d2, with their magnetic moments like this. Dipole moments are in this direction. Imagine d1 d2 d3, the dipole moments are in this direction, so that the net resultant dipole moment is absolutely zero. Imagine like that, because of their net resultant dipole moment is zero. And once you introduce the magnetic field to those cases, to those objects, what will happen is that there will be a domain growing or domain growing concept. What is a domain growing concept? Means whichever domains are having their dipole moment in the direction of the magnetic field, those dipole moment or those magnetic moment will grow, and whichever dipole moments or magnetic moments are facing opposite to the direction of the magnetic field, those magnetic moment, its value will reduce. So what will happen is that if I am drawing it as in a different manner to express that, say like this. Initially, imagine all the magnetic moments were of the same strength. Suddenly, you introduce the magnetic field in this direction. What's going to happen is that those which are pointing towards right will be having, those which are pointing towards right will be, its magnetic moment will increase like that, and those which are pointing in the opposite direction, its magnetic moment will reduce, and those which are on the other direction, it will try to direct towards the external magnetic field, and thus it shows some kind of magnetism. Okay, it shows some kind of magnetism, which we can say it as among the paramagnetic group. Now let's focus the magnetic materials, and let's arrange them according to their different material type. Say ferromagnetism. What is ferromagnetic substance? They are having a permanent magnetic moment, which they have an intrinsic permanent magnetic moment, which means ferromagnetic materials already have an intrinsic magnetic moment in a particular direction. Okay, so they definitely have a magnetic moment in a particular direction. So there is nothing to bother about that, because those materials already have a magnetic moment in a particular direction. Now when it goes to paramagnetic substance, what is the specialty of paramagnetic substance? Paramagnetic is compared to ferromagnetic, it is weaker, and we know that ferromagnetic moves from weaker field to stronger field. In the case of paramagnetic, it does the same. It moves from weaker field to stronger field, weaker field to stronger field, weaker field to stronger field. The main difference between ferromagnetic and paramagnetic is that these both are magnetic materials which show magnetism in their response to external magnetic field. They move from weaker to stronger field, but the already existing magnetic moment value for ferromagnetic and paramagnetic is different. In the case of ferromagnetic, that dipole moment is large. Okay, that dipole moment is large. So let me write it as large dipole moment for ferromagnetic substance, and the resultant dipole moment for paramagnetic is small. That's the main difference, small dipole moment. So that response you cannot expect as such as that of the ferromagnetic. That reflex action towards the external magnetic field will be slightly slower than that of the ferromagnetic, but that's fine, still it is magnetic. But we have a third group, which is diamagnetic substance. This is something which you should know. Diamagnetic substance. We know that this diamagnetic substance move from stronger field to weaker field. And how does that happen? So we have studied all the cases of other magnetism like ferro and para, but something that moves from stronger field to weaker field. How exactly the physics is happening in this case? So let's check the diamagnetic substances. Okay, in the case of diamagnetic substance, what exactly is happening is that the magnetic moment of an atom, remember the magnetic moment of an atom is that which gives magnetism to any material. So magnetic moment of an atom itself is zero in the case of diamagnetic material. That's what's happening. So if you take the magnetic moment of an atom is zero, and when you bring such a material into the external magnetic field, what will happen? There will be induction. Magnetic induction will occur. And what will happen to the atom? The atom will become magnetic. So that's what's happening. So in the presence of external magnetic field, when you bring a diamagnetic material, that diamagnetic material is induced with magnetism from the external field. Okay, induction is happening. When induction occurs, what will happen? When induction occurs, there will be an induced current in the diamagnetic material. And what does this induced current will bring? Induced current will bring another magnetic field. It will bring another magnetic field in such a way to oppose the main magnetic field, that is Lenz's law. Did you understand? So we have a diamagnetic material in which its atomic dipole moment is zero. To that we are bringing the external magnetic field. Once you bring the external magnetic field, what will happen? There will be magnetic induction, and that magnetic induction will induce a current which can create a magnetic field in the opposite direction of the main magnetic field. Now you might be confused that why it is not happening in the case of paramagnetic or ferromagnetic. Let me make it very clear. In these two cases also there is induction happening, and due to the induction happening, induced current is forming. Due to the induced current, an opposing magnetic field is creating. But the problem is, it's not enough to oppose the main magnetic field. Why? Because it already has an intrinsic magnetic moment. In such a way that it gets aligned with the main magnetic field. Now, when a small dipole moment is forming in the opposite direction, the resultant of this 1 and 2 is still in the direction of the main magnetic field, and that's why it's not getting repelled. So in the case of ferromagnetic, let me say that the intrinsic dipole moment is very high compared to paramagnetic, and the magnetic moment formed due to the opposition of the main magnetic field, it's very small. So the resultant magnetic moment, let me draw like this, is still in the direction of the main magnetic field, and now it's not opposing. But that's not the case of diamagnetic substance. Diamagnetic substance is having initially itself their magnetic moment is absolutely zero. Now, because of the presence of the external magnetic field, there will be an induction, and that induction will create induced current. That induced current will create a magnetic moment in the opposite direction. Now, who is leading? The one which is in the opposite direction is leading, and because of that, a diamagnetic material moves from stronger field to weaker field. Now, hope you understood the clear mechanism of magnetism. This is how it actually works. So you should know that how basically stuffs are working. Then only you will understand the proper physics. Okay, so now we understood ferro-para-dia. Now let's heat it up, the ferromagnetic material. So take a ferromagnetic material. Okay, now apply some heat. What's going to happen? What's going to happen is that its domain structure is going to destroy. It will curl up. Okay, if imagine the domain structure is like this, it will curl up and it will become closed loop chains, and thus it will lose its free pole nature. So initially there was a free pole nature, let's say it as north and south, whatever, but whatever, once it is becoming closed chains, then that free pole nature is getting destroyed. So once its free pole nature gets destroyed, then the pole strength is reducing. The ferromagnetic will become paramagnetic at a particular temperature. We call it Curie temperature. So when you heat a ferromagnetic substance, it's going to become paramagnetic at a particular temperature. We call it as Curie temperature. The explanation I have mentioned. The free pole nature is going to become closed chains. Now, there is a question that whether if you cool a paramagnetic substance, whether it is going to get a ferromagnetic back. Most probably yes, but not all the domains dipole moment you are going to get it back to the same position. That is because you have already made the alignment change. In the case of a paramagnetic, if you cool it up, then you are going to get back the magnetic material, but not exactly in the same dipole moment initially it had, whatever. Now, the another question is that if you heat a paramagnetic material, what you are going to get? Are you going to get a diamagnetic material with completely no magnetism? No. Why? Because a paramagnetic material, its definition itself is a substance which is having an completely unaligned or disordered alignment of magnetic moment. So the material stuff itself is having the intrinsic magnetic moment. The diamagnetic is something different, that there is no intrinsic magnetic moment in the atomic scale itself. Okay, so paramagnetic structure have domains, and these domains magnetic moment are disordered. So when you heat a ferromagnetic to paramagnetic, what's happening is that the domain, in the case of ferromagnetic, it's completely aligned. So once you heat it up, these alignments are going to get disordered due to the vibration of atom. Okay, vibration of atom. Due to the vibration of atoms, then the alignments are going to get disordered, and that's how it is becoming paramagnetic. So when it becomes more disordered, it's not going to become diamagnetic, it's still a paramagnetic. So the question is how we are going to make a diamagnetic material. Diamagnetic material can be made because of its, first of all, of its the internal nature of the material itself is the main reason for the diamagnetic, because its atomic dipole moment should be zero. Such materials should be chosen. Okay, and what is the specialty of this diamagnetic material? They can expel the external magnetic field. If it can expel the external magnetic field, if you keep say an object of, say if you keep a diamagnetic object and you bring the magnetism below, in an external magnetic field. Imagine the external magnetic field is in this direction, then it will completely levitate because it will expel the main magnetic field. It will expel the main magnetic field, and it has got the property of levitation. That's what you're going to see in superconductors. Superconductors levitate. Superconductor is an ideal diamagnetic substance which has the ability to levitate. The reason for superconductor to become is because of its extremely low resistance, which is actually created by reducing the temperature for few conductors few set of conductors, you reduce the temperature. Reduce means not you go and keep it inside the fridge, but you have to reduce it in absolute low manner so that its resistance will reduce. How its resistance is reducing? Because we know the formula, which is R2 equal to R1 into 1 plus alpha into delta T. So for materials like metals and conductors, the temperature coefficient of resistance is positive. So once you reduce the temperature, R1 will get reduced to R2. Once the resistance reduces, you know what will happen. The ability for the current to flow will increase. So imagine a point when R2 becomes 0. That is at the temperature when it becomes a superconductor. So once it becomes a superconductor, that is absolutely low resistance, then what will happen? That when you keep such materials in the presence of external magnetic field, okay, imagine I have a superconductor and I am keeping it in the external magnetic field. What will happen is that there will be induced current forming on the surface of the superconductors. Induced current forming on the surface of superconductors, we call it as Meissner effect, okay, which is not there in the syllabus, but for the information I'm telling. And these surface currents will something like eddy currents, you can compare with that. These kind of eddy currents, what will it do? It's create a magnetic field to oppose the main magnetic field. Okay, we have the main magnetic field over here, and these superconductors will oppose the main magnetic field with its induced current magnetic field, and thus it will levitate. That's how it is levitating. That's how it is becoming diamagnetic and expelling from stronger field to weaker field. So this is how it works. So now the last thing is that even if you are increasing the heat for a ferromagnetic substance, when you heat a ferromagnetic substance, we know that its magnetism is losing. So how come the earth is still having a resultant magnetic field, or earth's magnetic field is still there? Because we know that inside the core, once you go deeper and deeper into the core, or deeper and deeper into the crust or mantle, whatever, what's happening is that temperature is increasing. So at a very high temperature, something like inside the core, how still magnetism is there? What the reason is? Because the answer for that is that in the outer surface of the core, what's convection currents are popping out. They have the ability to produce the electric current, and this electric current can create magnetic field, and this magnetic field is what we call it as the earth's resultant magnetic field. So yes, even if you heat it up a material, still magnetism can prevail because of the convection current method. Okay, now right now we understood that the three magnetic materials, which are ferromagnetic material, paramagnetic material, and diamagnetic material, and its theory. Okay, hope it's very clear for you. Remember one more point, let me add it to it, that in the case of superconductors, when you mention the case of superconductors, we reduce the temperature. While reducing the temperature, electrons will get an additional property of attraction, not repulsion. We call it Cooper pairs. Okay, Cooper pair formation, once again out of syllabus, but just letting you know that the formation of Cooper pairs. Okay, now so we studied that ferromagnetic and paramagnetic are magnetic materials. Diamagnetic is a non-magnetic material and it expels from the magnetic field. And we know in the case of paramagnetic material, the susceptibility factor is inversely proportional to temperature. But in the case of diamagnetic material, it is independent. It is not at all depending upon the temperature. It's not going to respond to the temperature. Okay, so that's how these materials work. So what is that suspense factor? As always in all other previous videos, it is a diamagnetic material. It is how a diamagnetic material works that you should know from this video. It's easy to study the ferromagnetic and paramagnetic, but you might not have heard about the mechanism of diamagnetic material, and that's exactly what we have focused in this particular video. Hope you understood and enjoy.